Recording in progress.
Yeah, camps on everyone. Let's start off. Hope everyone has gone through the notes. The last thing that we did was cost loss. Great. There. So we'll be starting with a new chapter, capacitors. So capacitors, right? When we do circuits mostly in the next class or something, that will match a lot with current electricity. So the starting part is anyway a little different. So let's start it off. So what's a capacitor in the first place? And others, you need to keep your cams on. So a capacitor, it is a device which stores energy in the form of electric field. So what is this basically? So think of like this, when you say, in a dam stores energy, right? When you say hydroelectricity or whatever. So what is this energy exactly? So when you say the water is storing energy, the hydroelectric energy, right? It is like the dam is storing energy in the form of gravitational potential energy, isn't it? A battery is storing energy in the form of chemical energy, right? So similarly, right, a capacitor is a device which stores energy in the form of electric field. So in the form of electric field lines or electric field. So what is this exactly? So let's do a thought experiment. Imagine a scenario like this. We have a conductor. Let's say it has some charge Q. And now when you look at the field lines here, there will be a lot of field lines. Now let's say you take this thing and connect it to a bulb with a switch and you're grounding it. Now let's say the moment you close the switch, what will happen? The moment you close the switch, the charge will start flowing from the conductor to the ground. So when the charge is flowing, that's what we call as current. So this system, right, if you see, this is how it would look. We got a bulb and you grounded this. You will notice the bulb will start glowing, right? The current starts flowing through the bulb into the ground. At the same time, you will notice the charge on the conductor is decreasing and the field lines are also decreasing. And eventually, you will notice this whole conductor becomes neutral. There'll be no field lines. The bulb will stop glowing. So there are no field lines and the bulb stops glowing. So just try to look at the scenario here. When you close the switch, the bulb was glowing. Great. As the bulb was glowing, at the same time, you also noticed the field lines in the region were decreasing. And when the field lines completely vanished, the bulb stopped glowing. Now, I don't know what is happening here, but somehow this gives you a feeling the bulb is glowing as long as there are field lines. Isn't that what we can think of? So that means somehow the energy, right, the bulb is getting is coming from the field lines. So this is just a thought experiment. You're getting it. So we know from here, we can conclude somehow that energy is stored in the form of field lines. We don't know how or why or whatever, but it's like, you can get that conclusion. You're getting it. So we observe when the switch is closed. And later on, we are going to prove a relation between field and energy also. But this gives you an idea, like somehow the energy is stored in the form of field lines. That means electric field lines are nothing but another form of energy. You can say like that. Field lines are nothing but a form of energy. So when switch is closed, the bulb glows, and at the same time, the field lines start decreasing. So from this, we can conclude. Now, we don't know the relation. It's like this. If a body is going faster, it has more energy. Make sense? We have a relation, right? But we know that velocity is somehow depending, or energy is depending on velocity. What is the exact relation that we don't know? So we can conclude energy is stored in the form of field lines. So to give you a little more context, right? Think of like this. When you say there's a charge plus Q1 and the charge plus Q2, and when you say potential energy is K, Q1, Q2 by R. So this is my question. Where is this energy? When you say potential energy is K, Q1, Q2 by R, where is this energy stored? Is this energy inside Q1? Is this energy inside Q2? Where is this energy exactly? This energy is not inside the charges. It is in the space in the form of field lines. So all these field lines which are spread from here to infinity is actually the energy stored. You're getting it. How is that being stored? We have no idea, right? But we know from this experiment, right, we can conclude that somehow this energy is, storing in the form of field lines. So that means in a region, if you have more field lines, means you have more energy, more electric energy. Is this making sense, everyone? You're getting it. So we don't have a proof. It is just like a conclusion. It is like this, let's say mom has brought, like 2 cakes, kept it in the fridge. You and your sister are there in the house. Evening, both the cakes are missing. And we are sure you didn't eat the cakes. Who ate the cake? See, we don't have a proof. You cannot prove it. Your mom thinks you both ate it and she beats you both, right? But happens a lot, right? So that way. Anyway, but everyone got the context here. So whenever you're saying there are two charges and there is an energy of the system, K, Q, and Q2 by R, the question comes this way, like, okay, so if these particles are having energy, where is this energy exactly? This energy is not on the particle or inside the particle. It is actually spread in the space. The field lines are energy, right? So if you take a body there and let's say if you give charge Q, so consider charge Q is given to a conductor. The potential of the conductor is proportional to the charge Q. More charge you give, more potential you get. And however, we know it is proportional to Q. Think about it, units and dimensions. We know V is equal to KQ by R. So dimension wise, it has to be Q power 1. It can't be Q square. It can't be Q cube or anything else, right? So, it's proportional to Q. If you remove the proportionality constant, we end up with Q is equal to CV. So this constant C is Q by V. This is called capacitance. So what capacitance tells you is higher the capacitance, the more charge you can store per unit potential difference. So if a device has a high capacitance, look at the word only, yeah? Capacitance, capacity. Higher the capacitance, we have higher capacity to store energy or higher capacity to store charge per unit potential difference. You can say like that. So we define a quantity called capacitance. So capacitance tells you, right, how much energy or how much energy you can store per unit potential difference. So how does this capacitance look like? You must have seen this in real life. Did you ever see this thing? Fan is not working properly. अरे उसका capacitor खराब हो गया. Ever heard this statement? So there is a white color thing. You go and replace that, and your fan starts going normally again. Or if you have ever broken a TV remote or a keyboard or something, you must have seen these orange ones and blue ones. Ever seen this stuff? And these are capacitors. So the blue ones are the most commonly used ones, and these orange ones are also used in circuits a lot. You have different types. These are the capacitors. So next time, right, when you go to electrical shop and ask him, right, give me a capacitor, see what he does. He takes that white color thing, it has two wires, he puts them in the plug, switches on, and he takes it out, and then he joins these two wires. You get a spark, fart karke. And then he will say, this is working, and he'll give it to you. So what he did, he took both the wires, he kept it in the plug, he charged the capacitor, and when you connected both the wires, you discharged it. You get a spark. So that tells you that the device is working. So this is how capacitors would look, the practical ones. So capacitor is a device which stores energy in the form of field. Capacitance is the value or the capacity, of that system to store energy. You can think of like that. So this capacitance is independent of charge and voltage. It's a ratio of Q by V. So if you change voltage, Q will change. Capacitance will not change. It's like this. F is equal to ma. If I increase the force, acceleration will change. Mass will not change. Isn't it? So m is a constant. That same way, Q is equal to CV. C is a constant. Capacitance is independent of Q and V. So if you mess up with Q or V, they both will adjust. C depends only on the material and the dimensions. So it basically depends on the geometry, material, dimensions of the system. The units are farad. I'll write in the next page. So this is the symbol for capacitance. Two parallel lines. This is the symbol for capacitance. C is the alphabet which we use. Units are farad. Farad is a big unit. Most of the capacitors are in the range of 10 power minus 6, 10 power minus 9 farads. But yeah, you can get a big capacitor also. But what is the physical significance of this? So whenever you think of, okay, what does it high capacitance means? Look at the word only, na? Capacity. It has a high capacity to store energy. The higher the capacitance, more energy can be stored per unit potential difference. Means if you have a capacitor 1 and a capacitor 100, if I give them both of them 1 volt and 1 volt, this guy will store 100 times more energy. Yeah, you can remember like that. So there. So we have got a new device called a capacitor. So far the story is clear. So simply, what does a capacitor do? A capacitor stores energy in the form of electric field lines. That's it. That's the main thing you have to remember. Now, before jumping into the capacitors, we need to talk about one more device, a battery. We will study about ideal batteries. Later on, we will see non-ideal batteries also in the next chapter. So what does an ideal battery do? Simple. It has only one purpose. An ideal battery, it is a device which maintains a constant potential difference across its terminals. This is the symbol for battery. This is a very important one. Huh? The battery keeps coming everywhere. So a battery ka symbol will be one small line and one big line. So there, this is how it looks, a small line and a big line. The big line is the positive terminal. The small line is your negative terminal. So a battery has only one purpose. Huh? It maintains a constant potential difference. For example, if someone tells you the battery ka voltage is V, the meaning is this. Most people think negative terminal matlab zero. It is not necessary it to be zero. If your negative terminal is X, then your positive terminal is V plus X. Are you clear? The battery simply is telling you it will make a potential difference of V. That's it. It does not mean the negative terminal is zero or the positive terminal is something else or something else. Let me show an example. Let's say we got a battery, 3 volt. Let's say this voltage is 1 volt. What will be the negative voltage? Think about it. The difference must be 3 volts. So if the positive is 1, the negative will be minus 2V. Got it? That's it. That's what it tells. The difference is 3. The potential could be anything. Let me take one more. Let's say we have a battery. Let's say this is grounded. This is 2 volt, or let's say this is 5 volt. Now, because you grounded this, this will be 0. This will be uh, minus 5. I can make the other way also. Wait. Let's say this is 10 volt and this is 5 volt. And then this guy would be 7 volt. So negative terminal can have positive potential also. You guys tell me about this. What if you have multiple batteries? The middle wire is grounded. This is 2 volt, this is 5 volt, and this is 3 volt. This point is 0 because it is grounded. Okay. What is the potential on the right hand side? This is 0 because it is grounded. What is the potential on the right hand side? So that is 0. This would be minus 3V. Right? What is the potential here between 2 and 5? If that is 0, this should be minus 5. If this is minus 5, then this should be minus 7. Are you clear with the numbers, everyone? That's what a battery does. A battery simply creates a potential difference. It does not mean the terminal is 0 or nothing. Battery does not know what is the potential. That's it. This is what a battery does. You do, no matter what you do, no matter how much energy you take, the battery will always maintain a potential difference. An ideal battery. A non-ideal battery won't do it. An ideal battery does maintain a potential difference. Again, hypothetical, they don't exist. TK works. This is your second device, everyone. So capacitor and a battery. Any doubt so far? All clear with this stuff? The basics are important. You need to understand all these things. Because how does a battery work? What does a battery do? Because same thing you're going to use again in the next chapter, current, later on in AC circuits, everywhere, the idea is the same. So in entire electromagnetism, right, we have 4 elements. One is capacitor, battery, resistor, inductor. Inductor comes much later, but resistor, capacitor, and battery are the three things we play around a lot. All clear with this? Any doubts? Shreyansh, Diksha, Utsa, Arya, Advait, Aditi, Tanishka, Vedika? Great, going ahead. Now, capacitors, we have primarily three types. The parallel plate capacitor. This is what we study extensively. Spherical capacitor. Cylindrical capacitor. In real life, most of the capacitors are cylindrical. Unfortunately, we study that is the minimum we study. We just study one formula and we just ignore the rest. So let's study the parallel plate capacitor. Like I said, remember the ending of Gauss law is the beginning of capacitor. See, entire electromagnetism, right? Unlike mechanics, where you can visualize things, the ball is rolling on a floor, the ball is flying in the air, the ball is having a collision. Unfortunately, in entire electromagnetism, the visualization is little difficult. I can't tell you to visualize electric field and all that stuff, right? So you need to know your standard models. You need to know the what is happening with each thing. So you have to remember a bit. So what is a parallel plate capacitor? Consider two parallel plates facing each other. Right, with a small distance between them. You know why the distance must be small? Fringe effect. You don't want to deal with the fields on the edge. So we have parallel plates, distance is d between them. D must be very small compared to the dimensions of the plate. To neglect the fringe field. In case you don't remember this, this we did in Gauss law, page 94. Great. Now let's connect a battery. So we have the two parallel plates. Now listen to the story, what happened. The story is important. And you're connecting with them with a battery. And what is the job of the battery? To maintain a constant potential difference. So this will be your positive terminal. This will be your negative terminal. The moment you connect a battery to a conductor, what do you think will happen? The electrons which are sitting in the conductor, they get attracted towards the positive terminal. The positive terminal will pull the electrons from the left-hand side and will try to push these electrons to the right-hand side. So these electrons are going and accumulating on the other plate. So electrons always will go from higher to lower potential because there are negative charge particles. But you can think of like this, the electrons are attracted towards the positive terminal of the battery. So electrons get attracted towards the positive terminal. So the battery takes these electrons and throws them out. Understand one thing. A battery does not create charge. Whenever you think of a battery, right, think of a battery like a pump. What does a pump do? You have a water tank with water. Let's say you have another water tank which is empty. And if you connect both of them with a pump or a motor, the motor simply takes water from one tank and pushes into the other tank. A battery does not create charge. Battery simply moves the charge from one place to another place. You're getting it? So you can think of like that. A battery is like a motor which is pushing the water. There should be water to push, right? So if you connect a battery to plastic plates, this is not going to happen because a plastic plate does not have free electrons. So you will not see any electrons moving. So get attracted towards the positive terminal and accumulate on the plate connected to the negative terminal. So the moment electron passes through the battery, it gains some energy and gets pushed onto the negative plate. This is what happens when you connect a battery to a conductor. The plate connected to the positive plate becomes positive charge. The plate connected to the negative plate becomes negative charged. So basically, the negative plate will gain more electrons and the positive plate will lose electrons. And as this is happening, what do you think will happen? As the electrons are moving away, this guy becomes positive, this guy becomes negative. As more and more electrons are going, at some point, all these electrons on the right plate will repel these electrons so strongly, the battery, right, will not be able to push the electrons at some point. You guys remember this story, which I told in Gauss law? Imagine there is a room. Imagine there is one more room. Initially, there are 50 people here and 50 people here. I'm standing at the corridor and I'm catching people and throwing them into the other room. Remember this analogy? Exactly the same thing is happening here also. The battery is taking electrons from the left plate and trying to push to the right plate. But as you push more and more electrons, at some point, there will be so much negative charge on the other side. The electrons, when they try to go, they get repelled and the electrons will stop moving. You reach a steady state. So there is a limit how much the battery can push. So eventually you will reach a state where this guy becomes plus Q and this guy becomes minus Q. The charge will be on the inner surface of the positive plate. This will be minus here. Outside will be 0 and 0. You reach a steady state. So this is what happens after a certain charge accumulation. There's a bit of a theory, but you need to understand what is happening, or else the whole thing will look like weird. The field due to the induced charges. So this plus Q and minus Q are the induced charges. Is strong enough to oppose the field due to the battery. So inside the battery, right, there is a field which is actually moving these electrons, and this field is generated due to chemical reactions. So we will not get into this. So the field inside the battery is a non-conservative field. So we'll talk about what is a non-conservative field later on. But just remember that. It's non-conservative and it is due to chemical reactions. So we will not get into that part. So battery does that somehow. So far the story is clear. So that means if you take two plates and you connect them with a battery, one plate will get plus Q, one plate will get minus Q. The charge has to be conserved. The total charge is still constant. Now you tell me, if I have two parallel plates and if I give plus Q and minus Q, do you guys remember the charge distribution? What is the charge outside? Total by 2. What is the total? 0, 0. So this should be plus Q and this should be minus Q. So that means when you connect these two plates with a battery, all the charge will be on the inner surface. Because initially the plates are neutral. This is plus Q, this is minus Q. So there will be a field between the plates. And what is the field between the plates? Sigma by epsilon, 2 epsilon into 2 times because there are two of them, which is sigma by epsilon. And what is sigma? Q by A epsilon. And the distance between the plates is D. And once we got this, in case you forgot, I'll just write it down. If you have two parallel plates, and if the charges are Q1 and Q2, the distribution will be Q1 plus Q2 by 2. This is Q1 minus Q2 by 2. Q1 minus Q2 by 2. So that we did in Gauss law. Then we use our potential difference. V plus minus V minus is equal to minus integral E dot dr. So here the limits will go from 0 to D because this is x is equal to 0, this is x is equal to D. This is E, which is Q by A epsilon dr. Integrate this. So you end up with the potential difference V is equal to Q D by A epsilon. And if you write this thing Q by V, which is A epsilon by D, and if you remember, Q by V is nothing but capacitance. This V is your potential difference because of the battery. That all the story that we did, it is to find the value of C. So there, this is what we got. So capacitance of two parallel plates is A epsilon by D. A is the area of the plates. D is the distance between the plates. There, everyone. This is your second formula actually. What is the first formula you need to remember? Q is equal to CV. This is your first formula. The second formula I taught you today, C is equal to A epsilon by D. What is the field between the plates? Sigma by epsilon. Or we can also write this thing as V by D. Both are right. You can note down this thing. So there, these are total three formulas so far. Q is equal to CV, C is equal to A epsilon by D. The field between the plates is sigma by epsilon or potential difference by distance, V by D. This is valid for uniform field. Quite useful. Whenever they ask you find the field between the plates, you need not find charge and do all that nonsense. You can simply do V by D and you'll get an answer. You can note down these things if you want. Q is equal to CV, capacitance, and the field. Just write it onto the side, you'll need it. Clear with this? Great. Let's see one simple question on this. Capacitance C is given by 8.85 microfarad. The distance between the plates is 1 centimeter. Find area of the plates. Capacitance is 8.85 microfarad. Area is 1 meter square. Find distance between the plates. The direct formula substitution, there's nothing there. Get them. Just putting it in a formula. There's something important there. Okay, let's see. So what is the formula? C is equal to A epsilon by D. So what is C? 8.85. Micro is 10 power minus 6. Area, that's what I have to find. What is epsilon? 8.85 into 10 power minus 12. Hope you remember what is epsilon ka value. By D is 1 centimeter, that is 10 power minus 2. We end up with A is equal to 10 power 4 meter square. You know how big is this? This is 100 meter ka square. Meaning take a plate of 100 meters ka side into 100 meters. A very big, right? It's almost 1/10 of a kilometer. So if you take such a big plate, how much capacitance you get? 8.85 microfarad. You're getting it? So increasing area to increase capacitance is not a good option. So if you want big capacitor, increasing area is a bad idea. Increasing area to increase capacitance is not economical. So yeah, that doesn't work. What about the second one? Both the cases have a problem. So we will talk about that. That's the main intention of the question. Same formula, C is equal to A epsilon by D. 8.85 10 power minus 6 area is 1. 8.85 into 10 power minus 12 by D. We get D is equal to 10 power minus 6 meters. Now, if D becomes very, very small, we get there'll be a charge leakage. We get a high electric field. I'll tell you what it means in the next page. We get a high electric field, which leads to dielectric breakdown. So dielectric breakdown is nothing but the charge will start leaking. So charge will jump from one plate to another plate. Not a good idea. Whenever charge leaks from one plate to another plate like that, right? Basically, that's your spark. And whenever you get sparks, you get really a lot of heat. And when you get a lot of heat, the circuit literally burns down. Charge leaks between the plates. Sparks are not a good idea. So what's happening here exactly? What is this phenomena? Dielectric breakdown. So again, we are hearing a new terminology now. And this is something, you must have seen a lot of times. We just don't realize it. So what's a dielectric breakdown? When you apply high electric fields, others do keep your cams on. When electric fields are applied in a medium, the electrons and the nucleus are pulled apart. You know, pulled away from the nucleus, ionizing the medium. So imagine a situation like this. So let's say we have a nucleus and we have an electron going in a circle. Now, when you're going in a circle, on an average, it feels as if the electron is at the center when you're very far. So this is a scenario when the field is 0. Now, if you apply a little field, this is what happens. The nucleus will get pulled to the right, and now your electron will not go in a circle anymore. It starts going in some weird elliptical orbit. The orbit gets shifted. I think I wrote reverse. The nucleus will get pushed to the left, and your electron will start going something like this. So the electron is pushed this way, the nucleus is pushed this way. You create a dipole. But if you apply a really high electric field, the force is so high, what will happen? The electron will simply come out of the nucleus. This whole region, the air, which is supposed to be an insulator, suddenly becomes conducting. And if the medium becomes conducting, the charge will simply, it has become like this. The two plates which are there, it feels as if, there's a wire between them. So the charge will start jumping across the wire. And where you see this thing? Ever seen thunder? Lightning and thunder? That's a dielectric breakdown. Think about it. Air is an insulator, right? Then how does electricity pass from atmosphere to the earth in the form of a lightning? So to get a lightning, right, you have a very high electric field. It generates almost 10 power 9 volts. We are talking something like 1,000 megavolts or 1 gigavolt. That's the potential difference created between atmosphere and the earth. Because of such a high potential difference, the atmosphere becomes conducting and the charge comes down to the earth. And how does the atmosphere become charged? When the atmospheric currents, right, pass through each other, the wind is literally, rubbing against each other by friction. The whole atmosphere gets charged. So the air currents keep it charged, right? And the charge keeps coming back to the earth. So at any point of time, there is somewhere on the earth, there is a lightning storm. Even at this point of time, somewhere a lightning bolt is falling onto the earth. Most of these things fall in the Pacific Ocean. Um, so there is a continuous charge leakage from atmosphere to the earth. So this thing, right, is called dielectric strength of air. So what decides when the situation will happen is dielectric strength. So dielectric strength of air is 3 into 10 power 6 volt per meter. Meaning if you apply 30 lakh volts across 1 meter, you get a lightning. So dielectric strength of air is the minimum electric field. So this phenomena of the particles becoming ionizing is called dielectric breakdown. Minimum electric field required for dielectric breakdown. Now look at the previous question we got, 10 power minus 6. That means if you apply even 10 volt battery, the field will be 10 volt by D, which is 10 into 10 power 6, which is greater than dielectric strength of air. The capacitor will not work. The capacitor will burn down. You'll get a lot of sparks and you get a lot of heat generated and it burns down. So how does that look like? Let's see. Looking will make things more clear. Look at this guy.
What's up, everybody? Welcome back to Malabar Tour, where safety is number one priority. And today we're going to
This guy
experiment
ka
with a
channel is
Udin
Russian hacker.
coil or Tesla coil and a
Don't worry about his
graphite
language; it doesn't understand. But so what he's showing you, right,
pencil.
is something
What
called
will
a Tesla
happen?
coil.
Graphite pencil.
Let's
Graphite
jump to that point.
pencil and Udin coil. Let's see what happens. Okay, let's try this in a jar. Whoa! It's just
So the thing which he has in his hand, right, it's called a Tesla coil. It can generate pretty high voltages. The one he is using, right, it generates around 50,000 volts. Right now, when you keep it so close to a pencil, the distance is very small, isn't it? A centimeter. So 50,000 by 10 power minus 2, that will give you around 5 into 10 power 6. That is more than dielectric breakdown of air. That's why you can see that spark. And you can hear the sound buzz. Karke. That's your dielectric breakdown. So when you see a lightning, right, you hear the thunder. The thunder is the dielectric breakdown ka sound. That the same sound you're hearing right now here at a smaller scale.
pencil.
And when you're getting a lightning like this, you're not supposed to touch it.
Whoa!
You get a shock.
Ow! That's painful. 50,000 volts is painful.
Look at this thing, huh? You will see something nice.
Wow, isn't it beautiful?
Look at this. This is nice, no? What is happening? Remember in chemistry, you studied graphite is a good conductor. So the current is passing from the left side and going through the graphite inside the wooden pencil and falling onto the ground. So all the charge is getting discharged to the earth. So the right side it is getting grounded.
Pencil is coming out to the other side. Let's put another pencil over here. Let's see what happens. Wow, look at that. This is so cool. It just going to the
So that sound you're hearing and the lighting you're seeing is this is a dielectric breakdown. And like I said, if you get sparks, you produce a lot of heat. And if you produce a lot of heat, you burn.
Look at this. This pencil just sliding up.
This is what will happen to your circuit if you get sparks.
Yeah.
This guy is having fun though. Yeah. That sound which you're hearing, right, is when you hear that sound, that is the meaning of that air is becoming ionized. I don't know, nowadays you don't hear this, but during when I was in school, right, we used to have these transformers and some of them are not that good. They used to leak charge. You can hear this sound when you're near a transformer. Buzz. You can literally see the sparks and lightning there. Everyone clear what is dielectric breakdown? Any doubts on this? So increasing area is not a good idea because it is too expensive. Decreasing distance is also not a good idea because there's a dielectric breakdown. So then how do you increase capacitance? So in the formula, A, epsilon by D, you can't change area, you can't change D, we can change epsilon by introducing a medium. That's your dielectric. We'll talk about that later. That is the end of the chapter. So that actually has uses. Any doubt so far? So just to write down this example, so let's say you connect a 10-volt battery. And let's say the distance is 10 power minus 6 meters. The field between the plates is V by D. It comes to around 10 power 7 volts. This is much higher. There will be a dielectric breakdown. So decreasing distance to increase capacitance is also not a good idea. Up to some extent, it is okay, but more than that, it leads to dielectric breakdown. So the dielectric breakdown and dielectric strength. Dielectric strength tells you about how much field you require to make the material conducting. All clear with this? Great. Now listen carefully. Yeah? There are few things now. Like I said, there's a bit of a theory. Once theory is over, we can do a lot of variations. What are all the formulas I taught you till now? Q is equal to CV, C is equal to A epsilon by D, field is equal to V by D. Right? These are the three things we learned. Next thing. Now, if you have charges on the plates, then they'll also attract each other, force between the plates. So if you have two plates, plus Q and minus Q, and we want to find the force between them. Remember, you cannot use K, Q1, Q2 by R square. That formula is derived for point charges. So what is the formula for force? Field into charge. So force on the right plate is the field due to the left plate. Remember, whenever you want to find the force, you have to find the field due to the remaining guys on you. You should not take your own field on yourself. So if you want the force on the right plate, you should take the field due to the left plate into the charge on the right plate. What is the field due to the left plate? Sigma by 2 epsilon. What is the charge? Minus Q. But what is sigma? Q by area. So we get minus Q square by 2A epsilon. Yeah. So this is a formula you can remember. The force between the plates is given by minus Q square by 2A epsilon. It does not depend on the distance. It depends only on the charge and the area, and the minus sign indicates attraction. This is your fourth formula, everyone. You can note it down. Here. Next thing, if you have force, you also have energy. That was the whole game, isn't it? We started the whole story with energy, that the system is storing energy karke. So we should find that energy stored in a capacitor. If you remember the scenario, so if you take an intermediate stage, before reaching a steady state, let's say this thing has plus Q, this thing has minus Q. See, suddenly the capacitor won't get charged. Yeah, it takes a very small time, a nanosecond, but there is still a small time delay. So let dq charge go there. So this is an intermediate stage. So before reaching steady state, as the charge is going through the battery, let the charge on the capacitors be small q. Finally, you will reach capital Q. Let charge on capacitors be plus Q. And let dq charge go through the battery. And we know potential difference between the plates is charged by capacitance. Means understand this thing. As Q is increasing, the potential difference is also increasing. Isn't that what is happening? Initially, when you kept the battery there was no potential difference. So battery is strong, it is pushing in. After some time, this will get some plus Q, this will get some minus Q. The battery ka voltage, I'll give you some numbers. Let's say battery ka voltage is 100. The small Q will generate 30 volts. Now, because battery is stronger, it will push more charge. Eventually, you will get some plus Q and minus Q. The battery is giving 100. These guys are also giving 100. Now they become equal. At this point, you reach a steady state. Isn't that the story? As you're giving more and more charge, the plates will get a potential difference. They start fighting with the battery. So we have taken an intermediate stage. So as the battery pumps more and more charge, the potential difference will increase more and more. So what is the energy stored? Energy is simply charge into potential difference. So energy stored is simply dq, charge, and potential difference across the plates. Which is integral q by c dq. Limits will go from 0 to capital Q. That's your final charge. This gives you energy stored is equal to q square by 2c. This can be also written as half cv square. This can be also written as half qv. How do we get that? Q is equal to cv, right? You can just put that and replace all that. So by replacing q is equal to cv, you can get all these formulas. So if someone asks you what is energy stored, q square by 2c, q is equal to cv, you'll get half cv square. Cv is equal to q, you'll get half qv. So they're not different formulas. They're all the same formulas. You get them by modifying the q value. There. This is your fifth formula. So what is the first formula? Q is equal to Cv. Second formula, C is equal to A epsilon by D. Third formula, field is V by D or sigma by epsilon. Fourth formula, force between the plates, Q square by 2 epsilon. The fifth formula is the energy stored. So as you're pushing dq, 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 you have to do more and more work. So this is the energy stored. But what is the work done by battery? The battery ka voltage is constant. Work done by battery is the total charge that goes through the battery into voltage, QV. Now, if you notice something, the battery is doing a work done of QV, but you're storing only half QV. So the heat produced is half QV. Half of the energy becomes heat. So whenever you charge a capacitor or discharge a capacitor, you always lose half the energy. And do you guys notice something here? This is not the first time you saw something like this. First time you encountered something like this in surface tension. Capillary. Work done by surface tension was mgh. Energy stored is mgh by 2. Half of the energy became heat. याद आया? Heat produced in capillary action. Second time you saw this was in elasticity. When you take a wire and stretch it, the potential energy stored is half Fe, whereas the heat produced here. Work done by external is half Fe, whereas energy stored is half Fe. The heat produced is half Fe. So again, half of the energy was lost. So this is one common trend, you will see across different chapters. that whenever you have a system, right, you lose half the energy. Generally, not always true, but generally. Is this clear, everyone? Now the question comes, why are you losing energy? Anyone? Chalo, mathematically it is understood. You're storing half and the battery is doing double, so half is lost and all story is great. But someone can think of like why you're losing energy. There's no resistance of wire. So there's no resistance. These are all good wires. So where is the resistance here? Did I say anything about R anywhere? So even without resistance, right, you're still losing energy here. That is the point. Remember, what did I tell in the beginning? The electrons from here are rushing through this plate and going here. So when they cross the battery or when they move, are they going slowly? No, right? They have kinetic energy. What happened to all this kinetic energy? They collide with the plates and they stop. So all that kinetic energy becomes heat. That is why you're losing half the energy there, right? But great, that is one. But I'll give you a general formula. Remember this, it will be quite useful. Whenever they ask you heat produced, initial energy plus work done by batteries minus final energy. It kind of makes sense. Think about it. You have 100 rupees. I gave you 200 rupees, but in the end, you only have 50 rupees. What happened to the remaining money? You lost it, isn't it? So that's your heat produced. Whatever you have initial plus whatever battery gave you, you're supposed to have that much. But your final was something else. So the difference must have become heat. So this is a general formula for heat produced. So quite a useful thing. The last thing in this is energy density. So energy density is simply energy stored per unit volume. Now, just now we saw the energy stored in a capacitor is half CV square. If you can play around this with modify this, we can write capacitance is A epsilon by D, and voltage can be written as E into D ka square. This can be written as half epsilon E square into A into D. A into D becomes volume. If you divide energy by volume, so this is your generalized formula. D energy by D volume. Even though we proved it for capacitor, you can actually use this everywhere. Is half epsilon E square. Quite a useful thing. This is called as energy density. So this tells you how much energy you can store in a unit volume. This is one of the metric they use to measure battery capacity. A lithium battery has a higher energy density capacity than a regular battery, like which you use in your house, the cobalt nickel battery. This E is your electric field. There. Now we have come to something here. Now going back to the starting of the story, what was the story? Somehow the system is storing energy in the form of field lines. And what did we get here? We got the energy stored in a region. Energy density is half epsilon E square. That means in a region, if the field doubles, the energy becomes 4 times. We got a relation here. We proved there mathematically that the energy actually depends on electric field. Is this clear, everyone? There. So that was the thing when we started the whole story, right? It is an energy storing device in the form of field lines. Yeah, we had a vague feeling. Yeah, it depends on field lines, but this is the relation between them. It is like this. I know if you go faster, you have more energy, but what is the relation exactly? Half mv square, isn't it? I know if you have field, you have energy, but what is the exact relation? Half epsilon e square. All clear with this? There. This is the entire theory of parallel plates. So just to brief it out, how many formulas we got? Q is equal to CB. C is equal to A epsilon by D. Field is nothing but sigma by epsilon. Sigma is Q by A or V by D. So field both are right. Then we got force between the plates is minus Q square by 2A epsilon. Energy stored is half CV square or Q square by 2C or half QV. All are right. Then we got energy density, which is half epsilon E square. E is the field there. These are all the formulas we derived, everyone. You should remember them. There is no way out. Examine, you don't remember all this stuff. That's what I said. These chapters are different from mechanics. And that's why they're actually easy because you know your standard models, you know all the regular formulas, you can handle them. And these things have high weightage, so works out. Clear with this. Take a break. Come back by 9:45. We'll continue from here. We'll see problems now. That's a lot of theory, but yeah, it was important. Any doubt so far? Anything that you're not clear, not convinced? Chalo, come back by 9:45. Chalo, let's start off, everyone. Let's see our question. We have an incline. Let's say we got a block here. Let's say theta is 45 degrees. Mu is half. Let's say m is 10 root 2 kgs. This is connected to a pulley here. And this pulley here is connected to two parallel plates. They're not touching each other. So, and these two parallel plates are connected with a battery. So if I show you the side view, I'll just magnify this. So these are two parallel plates. So the upper plate is connected to the pulley, the string, and the lower plate is connected to the ground with a string. So string is non-conducting. And you're connecting these two with a battery of voltage V. D is the distance between the plates. A is the area of the plates. So the question is, find, I can give you numbers here also. Find voltage of the battery if the system is at rest. And I'll give you a little more context. Imagine there is no battery. So if there is no battery, what would happen? This green plate will go up, this plate will fall down, and the block will slide down, isn't it? That's what would have happened. Because there is a battery, there is an attraction between the plates that is actually keeping the plates from moving away from each other. There, see, that is how we connected. Force between plates is connected to resistance friction ka problem. That's what I'm saying. You will see force, energy. Once you got those, it's all mechanics again. Let's give it a try. Just get me the equations. Anyone not clear with the picture, didn't understand what is the question, please ask me. And you're thinking like, oh, this is something new and all. This is not new. You have seen this question two times till now. The first time you saw this thing was in friction. This problem, yaad hai? There's a block of 10 root 2 kg. There's a small m. Find m if the system is at rest. The second time you saw this thing was in electrostatics. Yeah, problem. Remember? There's a plus q and a plus q. Find the x when the block is at rest. And every time, remember, there was always a range of answers. You always get a range. You don't get a single answer. Since friction can change direction and can change magnitude, you get multiple answers. The story is clear. Just get me the equations. I'll give you a minute more and then I'll show you. That's it. Once you got that, there's nothing there. Means if you apply too much voltage, the plates will attract so strongly, the block will go up. If you apply very less voltage, the plates will attract weakly, the block will come down. So there is a maximum voltage and there's a minimum voltage. You get a range of answers again. So whenever you see the word friction and equilibrium, you always get a range. Just get me the equations. Okay, let's see. So let's say if you apply a maximum voltage, what would happen? The block will try to go up. It tries to go up. So now when you draw the free body diagram, you will see the forces will be mg sine theta. This will be F max, which is mu mg cos theta. This will be your tension. This tension will go to the plate. This will be the tension. This will be the plate. And the plate is attracted by the other plate, q square by 2a epsilon. And remember, Q is equal to CV, which is A epsilon by D into V. That is a relation between Q and voltage. So there you're done. So this would give you Q max. So Q square by 2A epsilon must be equal to mg sine theta plus mu mg cos theta. This is your Q max. So if you solve this, you'll get a V max. Yeah, you can do that. I will leave it to you. Similarly, if you apply minimum voltage, meaning the attraction is so weak, the block will try to slide down. We have tension. This time the friction will be upward. Mu mg cos theta. This would be mg sine theta. You have seen this. This is the third time already. The story would be same on the right hand side. This would be again q square. This will be q minimum to a epsilon. Q minimum square by 2a epsilon is mg sine theta minus mu mg cos theta. You solve this, you will get V minimum. So your answer will lie between V max and V minimum. That's the main thing. You should realize you'll get a range. If you got that, your job's done. All clear with the process. So the only thing you used is q square by 2a epsilon. Everything else is friction ka problem only. Any doubts on this? All clear with this? Tanishka? Clear? Srihari? Shriyan? Shaurya? Clear? Next thing. Did you guys start using the Telegram ka bot? From the day I told you until now, it got upgraded a lot. You can go and check it out. If you keep sending data, you'll start getting insights also. It'll start showing you. And I'm looking at the data every day. I have a separate tab. Whatever you're typing, I can see. So in that end mate, there is a note, you have an issue, you're facing something, you can always type there. I'm reading everything. Right? And at the end of the typing the report, if there is a link which is getting a dashboard. If you click that dashboard, you literally get to see what you have studied last week, everything. Right? It will still get upgraded going on. So for now, it is still going on. So it took time. I think I spent almost 20 hours building it. So dashboard is still not working for you. Maybe you can write anything in that notes, like anything other. Don't write a story there or something. It's about like what is happening, like what are you facing difficulty or weak points or whatever you put there. So there is a tab there. Okay. So that is how it is. What do you guys think I was doing in the holidays? I gave you a break and I was sitting and doing all this. No, it was fun. It is all. I was using what? I used Gemini and Claude. So think about it. Huh? People keep saying AI, AI. AI means it is nothing. I'll tell you what I understood from whatever I did. It is the future. There's no doubt about it. But this AI is simply, think of like this. It is an assistant, right? You want to hire an assistant like AI. It is a 50, imagine you have to pay 1 crore salary to a person. You have such a powerful assistant who is very capable, whose salary is 1 crore per year. Such a powerful assistant, right? Now you can get scared that the assistant might replace you, or you can think you can use this assistant to build much better things. People are getting scared. People are not seeing the utility of it. Getting it, it is all about the AI can't think about itself. Think about it. Who the hell will think someone will use an Claude Gemini to monitor your guys' homework? See, I thought about it, right? Because I'm seeing it. I said, yeah, I can use this way. Because when you guys are sending so many reports, I am not able to read all of them. After reading, also, I'm forgetting, right? What you sent 2 days back, I don't remember what you sent today. I'm unable to see like whether are you actually studying all the subjects or not. There was one time I saw a certain report. For some reason, I just started scrolling back all the reports and I noticed the kid is not doing max from 2 weeks. They're not touching max only. Every day they're sending a report, they're studying. I was reading a report and I was feeling like, acha kar rahe, acha kar rahe. But after a week, I realized, boss, this guy is never touching max. And when I asked him why you're not doing max, and the kid says, sir, बहुत tough जा रहा है, so I'm not doing it. So what is the point, right? And इस बार तो वही हुआ ना advanced exam में. Chem and physics was hard, max was actually manageable. And then you can have your favorite subjects, but should not ignore a subject to that level where if you get easy questions also you get scared. So yeah, that happens a lot. You guys are all an online batch, right? Why will you opt for an offline? Uh, get in the online batch. Okay, so that's it. So don't worry too much about all these people talking about AI and all that bullshit. It's all about if you have brains to think, right? The only thing what people are worried, I'll tell you what is happening. The work, right? The work which used to take you 20 hours to do, if you are capable of using an AI, you can get it done in 2 hours. Again, not all the work, certain works can be done. Now you have a bandwidth for 18 hours, you don't know what to do with that 18 hours. Means now you have to give more work to that AI. Keep saying, boss, ye karo, ye karo, ye karo. So if you're capable of thinking, if you're capable of visualizing to build stuff, it's really powerful. You will, yeah, it's like, you're unbeatable. Like whatever work I did building that, almost 18 hours, 20 hours. I'll tell you one thing, I know zero about coding, okay? I don't know anything about coding. Whatever coding I did it 16 years back when I was in college. Now I don't remember anything. That whole thing which I did, a complete newbie, right, took 16, 18 hours to build it. A professional who's very good would still take 2 days to build it. Now, imagine the professional can use this thing. He would have built it in an hour. So yeah, it's a multiplying factor. So keep working hard, right? Don't ignore stuff. Keep your brain sharp. Think. That is the main thing. You can think, you can keep your brain sharp, keep your work, and then it is just a tool. It will really make you go places. It's like people using, a typewriter and then a computer. When computer came, people who are very good in typewriter got extinct. Now people who know very well computer, but they don't know how to use AI, they'll go extinct. So it is a normal phenomenon. There's nothing new about it. When alarm clocks came, in 1920s and 18s, there is a profession of, there are people used to come to your house and wake you up in the morning. These people are alarm clocks. You used to pay money every month, for them to come and wake you up. If you're staying in the first floor, they'll come to your house. They have a big stick. They'll knock your window with that stick. That was a job, waking up people in the morning. Then, anyways, but please try to use that bot. It helps. I'll keep upgrading more, right? Again, I'm telling you, it is not for me. It is for you. It will keep a track of what you are doing. And I also added a feature there. It will compare what you did this week with last week. So it's a competition with yourself. It'll tell you how much well you did compared to the last time and so on. So anyway, there. So we got two capacitor plates. This is the battery B. This is your switch. We got a non-conducting spring. So we got two parallel plates and you connected a spring between them. This spring is in natural length. The distance between the plates is D. The area of the plates is A. And this right side plate is fixed. The left plate is movable plate. So when you close the switch, the plates will get plus Q minus Q. Because of that, the plates will start getting attracted. And when they get attracted, what will happen? The plates will come closer. The distance between them changes. When switch is closed, the distance between the plates becomes 0.8 D. Initially, the distance was D, now it becomes 0.8 D. Find the voltage and the heat produced in steady state. Technically speaking, the spring will actually oscillate. We're not doing that. Something happened, it reached a steady state. Find the voltage of the battery and find the heat produced. Again, let's understand the story there. Initially, the switch is open, so there is no charge. The moment you close the switch, this plate will get plus Q, this plate will get minus Q. The plates will attract. If the plates attract, the spring will compress. The springs will make sure the plates don't come towards each other. As the plates coming closer, 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 the distance became 0.8 D and the plates came to rest. Is the story clear? Using this information, you had to tell me what is the voltage of the battery and how much heat is produced in this process. There, let's get this. I hope you can see how the questions are being framed. Even though we say capacitors, there is still mechanics involved everywhere. Mechanics is not going to leave you. Let's give it a try. I'll give you 2-3 minutes. Think about it. It's a pretty good one. And you know your formulas, right? Q is equal to CV. C is equal to A epsilon by D. Force is equal to Q square by 2A epsilon. I hope you wrote it down. So you just need to know those formulas and you'll be done. Give it a try. Anyone is confused with the question, didn't understand the picture, please ask. Mm, 4.5 D. Okay, looks right. Get the heat produced. Heat produced, just write the equation. Once I write, you can verify. That looks right, Samyak. Let's see. Try. I'll give you a minute more, everyone. Everyone should try. It's okay to get a wrong answer, but get something. Just think about the final picture, how it looks. Remember the distance became 0.8 D now. 0.4 D, एक D क्यूब आएगा रे. Let's see. So let's draw the picture first of all. So when the switch is closed, the distance becomes 0.8 d. So multiple things happened here. First thing, what is the capacitance? Capacitance is A epsilon by 0.8 d. Remember, capacitance changed. What is the charge? Q is equal to CV. So what is the force? Force is equal to Q square by 2A epsilon. Hope this part was clear. Next thing, draw FBD of the left plate. The right plate is anyway fixed, so there's no point in drawing it. If you draw FBD of the left plate, there are two forces. The spring is pushing. What is the spring force? K into X. What is X? Compression. This is 0.2 D. Be careful. If the initially distance was D and the final distance is 0.8 D, the difference is 0.2 D is the compression. And the spring force? Q square by 2A epsilon. Since you're in steady state, these two must be equal. So Q square by 2A epsilon must be equal to 0.2 kd. But what is Q? Q is CV. But what is C? A epsilon. So that will be A square epsilon square 0.64 d cube into V square by 2A epsilon is equal to 0.2 kd. Yeah, you can solve this. You'll get V from here. So that's 0.2, 0.64, 0.4, 64, 4, 256. So yeah, I'll leave it to you. You got it. Clear this 0.256 K ये d square था ये d cube by a epsilon. Something like this. Check it out. All clear with this? What about the heat produced? Remember the formula. Heat produced was initial energy plus work done by batteries or any external force minus E final. What is the initial energy? Zero. There is nothing there. Work done by battery, Q into V. Work done by external, zero. What is the final energy? Final energy has two parts. Half CV square, capacitance, plus half Kx square, the compression energy in the spring. So half CV square you know, and half Kx square is half K 0.2 D whole square. So there's a spring potential energy and there is a energy in the capacitor. There. So the heat produced will be QV minus half CV square minus half K 0.2 D square. That is officially actually half QV only. So if you see here, heat produced is less than 50% because some of the energy went into the spring. That's what I said. Every time it's not necessary to lose 50%. Is this clear, everyone? Any doubts on this? Any confusion on this? There, see what did we use? Q is equal to CV, we use the force formula and we are done. Let's see one more. This one, next one is a good one. This will be a pretty good mains level question. Let's say we have a capacitor C connected to a battery. Voltage V. So initially you will have some charge plus Q and minus Q, where Q is equal to CV. Great. Now what you did, case one, the battery is removed. You remove the battery. Now, when you remove the battery, what happens? The charge remains constant. There's no way charge can go anywhere. Case 2, the battery is present. So you did nothing. You just left it as it is. So whenever you keep the battery, what does the battery do? It maintains a constant potential difference. So without battery, the charge has no place to go anywhere. With the battery, the potential always has to remain same. Now in both the cases, case 1 and case 2, the distance between the plates is doubled. So case 1, remove the battery, double the distance. Case 2, keep the battery, double the distance. I hope everyone is getting the two scenarios. Then what I want you to find is this. In case 1, what will be the new charge? What will be the new capacitance? So you have to tell me like this. If initially it is Q, will the final remain same, double, becomes half, becomes 4 times, like that? What happens to the new voltage? What happens to the new force between plates? Or let's call field. Force between plates. Energy. Energy density. There, total 7 questions. And 2 cases. So total 14 questions. Are you guys getting what I'm asking? If initially voltage is V, what is the new voltage? It will be double. If initially field was Z, now what happens? It becomes half. Initially force was same, now it is also same. So I just wanted the ratio basically. Compare initial and final. Take a minute, think about case 1. If you're still confused, I'll show you case 1. I'll give you time for case 2. So I want you to tell me what happens to the charge, voltage, field, energy, and so this will cover literally all the formulas. New force, new energy density. There, give it a try. It's a good one. Once you double the distance between the plates, how will the 7 quantities get affected? Try. Okay, let's see. I'll show you the first ones in case you're confused what I'm asking. Let's do it. I know there are too many things I asked, so it could be a little overwhelming. So let's see case 1. So case 1, you remove the battery and you double the distance between the plates. Great. So first thing, whenever you get these kind of questions, right, start with capacitance. Start here because capacitance does not depend on distance, anything. So what is the capacitance ka formula? A epsilon by D. Since the distance became double, capacitance becomes half. So this becomes C by 2. Makes sense? If initially it was C, now it is C by 2. Second thing, since the battery is removed, charge remains constant because there is nowhere for the charge to go. So if initially charge is Q, finally charge is also Q. You can write same. You can write here it become half. Great. What is the voltage? Q by C. Q remained the same, but capacitance became double. So voltage also becomes double. Field is voltage by distance. Voltage became double. Distance also became double. So this remains same. Force Q square by 2A epsilon. Q didn't change, A didn't change, so same. Energy का formula. I'll use Q square by 2C because Q remained same. Q is same, C became half, so energy becomes double. Energy density, half epsilon E square. Field remained same, so energy density also will remain same. Are you clear what I'm asking? Is everyone clear what we did? Any doubts on the 7 parts, please ask me. So it's a comparison before increasing the distance, how it was, and after removing the battery and increasing the distance, how it was, and then you say. All got an idea here? So using this, can you do for case 2? Same story. Battery is present, distance becomes double. Can you fill up this table? Try. I'll give you a minute. This is a good one because there are like 14 questions in 2 parts. They can ask any one or two in mains. Okay, let's see the second one. So when you keep the battery, remember, battery will keep the voltage same. कुछ भी करो, voltage will remain same. That is the point of a battery. So in a way, it's a very good one. So if you remove the battery, the charge has no place to go anywhere, so it will remain there. If you keep a battery, the voltage will remain same. So voltage will remain same. V capacitance will become half. Same story. The charge becomes Q is equal to CV. So this becomes Q by 2. So this becomes half. This becomes half. This remains same. Field is potential difference by distance. Potential difference is same. Distance became double. So this becomes half. Force is Q square by 2A epsilon. Charge became half. So this is 1/4. Energy, I can use half CV square. See, nothing wrong. You can use Q square by 2C also. I'll use half CV square because V is constant. Capacitance became half, so this is also half. Field became half. So this becomes 1/4. Check your answers. All clear with this? Yeah, clear with this. We will see something similar again later on in the same chapter. The next one. Next one is a good one. This was it actually came as a PYQ advance. I modified it. I made it even more little better. So let's see. Let's say we have two parallel plates. This thing has a charge Q1. This thing has a charge Q2. Both are connected by a switch. C is the capacitance of the system. Now let's do this. I'll show you what is the actual question J gave. Find the voltage, find the potential difference between the plates before the switch is closed. Find the heat produced when the switch is closed. Now, before going ahead, I want to ask you something. When you say there is a capacitor connected to a battery, whatever, when you say capacitance is C, can you guys tell me exactly what is the capacitor here? When you say this is the capacitance C, are you talking about the plate? Is the plate is the capacitor? What is a capacitor here? Remember, capacitor is a space where electric field lines are present. The space between the plates is the capacitor. The plates are not the capacitor. The region between the plates where the electric field is present, that is the region where energy is stored. That is the capacitor. Are you getting it? If I ask you, what is your room? Is the walls the room? The walls are the boundary of the room, isn't it? The space between the walls is the room. The space between the plates is a capacitor. The plates are not the capacitor. Let's do this. Now, this is where people get confused. Like I gave Q1, Q2. So how do we do this? Right over here. Get the second part also. You got the first part right. Something similar they asked in advance, and people got confused. They thought, "Are Q is equal to CV." Now they got confused. Should I take Q1 or Q2? They didn't understand. So that's because you really don't understand. Like when you say Q is equal to CV, what are you talking about? What is Q exactly there? Right, Samyak? Think. Others think. Give it a minute. It's a good one. It's a good theoretical thing. Okay, let's see. So let me ask you a few questions. Let's stop from there. When you say Q is equal to CV, what is this Q exactly? Is Q the charge on the capacitor? Or is Q the charge on the positive plate? Because this we have to be clear. If you say Q is the total charge on the capacitor, this is plus Q, this is minus Q. Total charge is zero, isn't it? If you say Q is the total charge on a capacitor, then the total charge is zero. Then you say, no, sir, Q is the charge on the positive plate. Is it the charge on the positive plate? So let's go back to the definition again. Let's go back to the proof. If you see the derivation, you'll understand. So when you took the two parallel plates, let these charges be Q1 and Q2. The charge distribution was outside was Q1 plus Q2 by 2. This was Q1 plus Q2 by 2. Here it was Q1 minus Q2 by 2. Here it is Q1 minus Q2 by 2. And because of these green thing, you're getting a field lines here. This E was Q1 minus Q2 by 2, that is the charge, by A epsilon. And then if you remember how we proved this whole story, this is what you said. So this guy, this charge was the responsible for the field. It's not the total charge. And if you remember the derivation, then you said the field into distance is the potential difference. Then we got Q1 by Q2 by 2A epsilon into D is equal to V. Then we got Q1 minus Q2 by 2 is equal to CV, because A epsilon by D is C. So when you're writing the formula, Q is equal to CV, remember this. Q is the charge on the inner surface of the positive plate. It's not the total charge. It's not the charge on a plate also. It is the charge on inner surface of the positive plate. There, that was the main thing you should know. What is Q exactly? Q, most people think Q is charge on a capacitor. You ask them what is the charge on a capacitor and they start thinking, okay, what is the charge on a capacitor? Are you clear with this? So what is the potential difference? Yeah, so the potential difference V is simply the charge on a capacitor is Q1 minus Q2 by 2C. Is this clear, everyone? What did they ask in GE actually? JMA question was this. They said there is a capacitor. It was connected to a battery. Then this thing had charge plus CV. Then this charge was minus CV. Then battery is removed. And a plus Q is given to the positive plate. This is what they did. This was actual advanced question. They gave additional Q charge to this plate, plus CV and minus CV. Then the question was find the new potential difference. Most people got confused. They didn't understand. In the formula Q is equal to CV, what was Q? Most people thought Q is the total charge on the positive plate. They wrote Q plus CV. But if you actually see that distribution, what is the total charge outside? Q1 plus Q2 by 2. That is Q by 2, Q by 2. Gauss law, people. And inside charge is Q by 2 plus CV. This is minus Q by 2 plus CV. So in the formula, Q by 2 plus CV is C into the new potential difference. So this is the charge on the capacitor. So V new will be V plus Q by 2C. That was the answer. This was the actual question in the advance. All clear with this? What about the heat produced? Question still not over. Now, if you close this switch, what will be the heat produced? Yeah, most of you got it. So you can look at the scenario here. This was Q by 2. This was Q by 2. So we have field lines here. And we have field lines here. Sorry, this was Q1 plus Q2 by 2, Q1 plus Q2 by 2. This is Q1 minus Q2 by 2, Q1 minus Q2 by 2. Now, the moment you close the switch, both of them will have same potential. If both have same potential, that means you cannot have any field lines between them. Because if you have field lines between them, you will get potential difference. So outside charges will be Q1 plus Q2 by 2. These will not get affected. But the inside charges become 0 and 0. The field between the plates becomes 0. Now, can you clearly see here what happened? The moment you close the switch, all the field lines in the middle vanished, isn't it? That means all the energy stored in that space vanished. So heat produced is simply the energy stored in the capacitor. So heat is simply Q1 plus Q2 by 2 ka whole square by 2C. So I'll write on the formula bit. Q square by 2C. So here Q is Q1 minus Q2 by 2 ka whole square by 2C. That's your answer. Q1 minus Q2 whole square by 8C. So all the energy stored between the plates, that is energy stored in the capacitor, becomes heat. All clear with this? Any doubts on this? Y minus the charge was Q1 minus Q2 by 2, na? The Q is the charge on the inner surface of the positive plate, isn't it? Outside is Q1 plus Q2 by 2. Those things were not affected. What vanished is the green one, isn't it? The green one is Q1 minus Q2 by 2. Clear? There. So in parallel plates, this is how you can play with energy. Any doubts on this? All clear with this? There. So that's a bit about it. So make sure to go through this. I know there's a lot of theory, but again, if you just go through them, derive it, check it out, remember the results. Next class, when we catch up, we are going to do something even more interesting, right? We're going to talk about this energy density, spherical capacitor, cylindrical capacitor, and we're also going to start with circuits. Circuits are very important. Exact same circuits you'll see in current electricity. So in the next first half of the class, we will play a little more with these equations and stuff, and then second half we'll start off with circuits. Okay, with that, we'll wrap up for the day. And do remember, Gauss law is over, electrostatics is over, gravitation is over. Please start solving, right? And if you see last two tests and this test, it's all electrostatics, gravitation, Gauss law. These things are only coming. So do solve them and do finish your material. Whatever you're solving, do finish your material thoroughly. Okay, with that, we'll wrap up for the day. I'll see you guys again on Thursday. Same time, we'll continue from here. So any doubts, anything else, please stay back and ask, or else you're free to leave.